Now it's my pleasure to introduce today's keynote speaker, Sarita Adve, Richard Teaching Professor of Computer Science at the University of Illinois at Urbana-Champaign.
It's a great honor to be here. Thank you for inviting me. So the title of my talk today is Enabling the Era of Immersive Computing. This is going to be work that represents the work of many, many colleagues, and I will be acknowledging them as I go along. So by immersive computing, we mean the seamless integration of the virtual with the physical. The holy grail, or the big grand challenge, is to have comfortable, mobile, all-day, trustworthy, rich immersive experiences. What do I mean by that? So imagine if all of our colleagues who couldn't make it here today in person could participate here in a mixed reality scenario where we can interact with them like as if they were here. They can interact with us like as if they were here as well. We are far away from such a reality. Now, by immersive computing, I include virtual, augmented, mixed reality, VR, MR, AR, AVR, AR, MR, extended reality, and I'll often use XR or extended reality interchangeably with immersive computing. Also include buzzwords like metaverse, spatial computing, digital twins, et cetera. So I believe that immersive computing is poised to transform most industries and all human activities. This includes healthcare, education, science, industrial design, manufacturing, maintenance, retail, entertainment, and of course, social interactions. So here are some example applications of immersive computing that are transforming various aspects of our own campus. This is a homegrown application at the University of Illinois that is used in our archaeology class, and the students use this to experience archaeological sites that they wouldn't have been able to experience in this way before. Here is, again, a homegrown application that is employed by our Fire Institute to train real firemen and in real scenarios. This is also an outgrowth from University of Illinois, where surgeons are using these technologies to perform pre-surgery planning. And then recently, we, in collaboration with the company MediView, brought in mixed reality into the operating room at the University of Illinois College of Medicine. Here is a faculty member and a student employing these technologies to understand how the acoustics of a room affect a voice performance. Here is the use of these technologies for a performing arts scenario. This is industrial manufacturing, maintenance, et cetera, and on and on and on. So I truly believe that if we could make this really work, we would be entering a new era of computing. And this is similar to the transformations that we've had as we've changed the computing modalities in the past. So we went from mainframes to personal computing, brought the computers home, changed how we interacted with computing. Same thing happened with the web and cloud, mobile computing. All of this led to industries that we would never have imagined, YouTube, Uber, et cetera, and now immersive. And who knows where this is going to lead us. Each of these eras was transformative. Each of these changed how we design, program, and use computers. I'm going to try and use the word AI as less as possible in this talk because we've seen so much of it in the last 4 days. But of course, AI is going to enable a lot of this. So what are the challenges and opportunities here? I talked about comfortable, mobile, all-day, trustworthy, and rich immersive experiences. Many of you will recognize the Apple Vision Pro, one of the nicer products out there, but comfortable it is not. And if you've ever used it, you know what I mean. So for example, if we look at the state of the art in terms of weight, the Apple Vision Pro is heavy, as are many competing products. So we're talking about 500 grams type of weight, when really what we want is a glasses sort of form factor, tens of grams, to really be comfortable all day. For power, the Apple Vision Pro is actually about 20 to 30 watts. The state-of-the-art glasses are about 7 watts. But where we really want to be to have all-day battery life and to have reasonable thermal dissipation on our noses and faces here is a few hundred milliwatts for compute, all of compute. For battery life, as I said, today's systems last about 2 hours. We would like to be able to walk around all day. And on and on and on. Resolution, there's orders of magnitude difference between what we have today and what we would like. Bandwidth, there's orders of magnitude difference. Collaborative users, there's a huge difference. And all of these orders of magnitude gaps between the current and what's desirable, we need to bridge these gaps with the envelope of very, very tight constraints. So for example, the motion to photon latency, which is all about how long does it take from the time the user moves their head to the time the image before the user changes to reflect their new perspective. This latency for VR needs to be around 20 milliseconds, whereas for AR, it needs to be around 5 milliseconds. That's a very, very tight latency. And so if you're thinking, hey, we're going to move everything to the cloud or to the edge and solve all these problems, well, that's not easy. It's going to be a big part of the solution, like I'll talk about, but it is not easy because these latency constraints are really hard to meet. And I haven't even talked about the bandwidth constraints here. If you took raw images, send them at 144 hertz, which is what desired display frequency is, you're talking gigabits per second. Of course, you apply lots of tricks to reduce that, but we're still nowhere near where we want to be in terms of today's 5G networks. What about the experience? So when the Apple Vision Pro came out, this is how, if you had a teleconference, these were what the personas look like, not particularly realistic. There was a really nice demo with Lex Friedman and Mark Zuckerberg that went around, and it was amazing. Very, very realistic avatars talking to each other in the metaverse was mind-blowing. And yet, these are just the talking heads in a dark room. This is not what we talked about in the beginning with our friends here as holographic images that are walking around and we're interacting with them in a natural way. So a long, long way to go to meet this grand challenge. And given the state of Moore's law, Dennard scaling, and all of the things that we know very well in this audience, unfortunately, there is no silver bullet, no one silver bullet that is going to make this reality, this potential come true. We need work in materials, we need work in devices, hardware, programming, runtimes, networks, distributed systems, security and privacy, graphics, vision, AI, sensors, optics, displays, audio, haptics, olfaction, chips to systems. This is your problem. Okay, so my goal here is to excite people to work in this area from this community far more than we see right now. All right, so that's the technologies. But technology is no use if we don't have applications, right? If you really want to democratize a technology, democratize applications, just like cameras on cell phones, et cetera, enabled videos, and that's what, that's why YouTube came along, and so on. So today, if I talk to my colleagues who built all those applications that I showed earlier, they will all say how difficult it is to get 3D content going and to get these immersive applications going. Now again, with Gen AI, this is a huge opportunity today for us to make a big change. Deployment of these applications is hard. Of course, there are all the technology barriers that we talked about. How do you assess how well these applications do is hard, and I'll talk about that in a bit. And what we really want is to create an ecosystem where new applications are really easy to build so that we can spark new industries that we don't even imagine today. And third is the human experience. Now, immersive computing is a modality that is, I guess in my experience, it's tied intimately to the human experience, far more than anything that I at least have worked with. And what do I mean by that? Well, there are two aspects to this. The first is, how do we experience these immersive technologies, right? If you've used some of the headsets, if you're lucky, you didn't get a headache, you didn't feel sick. But if you're one of the unlucky ones, well, you know what I'm talking about. Not only that, but as a system designer, when I am changing, optimizing, as I will show you as we move along in the talk, sometimes the metrics, or often the metrics that we use to measure the goodness of the system don't quite match up with the experience of the user. And so there's a lot going on here. There's cyber sickness, of course, but there's psychological issues, there's neural stuff, there's behavioral aspects that we need to understand, and of course the design and usability and ergonomics of all this. So we don't quite fully understand many of these concepts, leave alone being able to measure them and then use them to improve our technologies. And as you all know, if you can't measure it, you can't improve it. So how do we measure the human experience with these technologies is a huge challenge. And the second aspect of the human experience is, how do immersive technologies change how we experience the world? These are contextual experiences, so how is this going to change healthcare? How is this going to change the industrial manufacturing floor, et cetera? And of course, the social experience. So this is going to change how we interact with each other. And as technologists, it is our job to ensure that we keep these things in mind. Privacy, ethics, policy, accessibility, inclusion, collaboration. What are the future spaces going to look like? We want to be able to think about all of this as we are building this technology. And so with all of this in mind and as motivation, we at the University of Illinois put together Immerse, which is the Center for Immersive Computing. It's a campus-wide center for immersive technologies, applications, and human experience for research, education, and infrastructure, with our goal to work with the community to enable the era of immersive computing. So this is truly campus-wide. It brings together people in engineering, the liberal arts and sciences, medicine, the School of Design, et cetera, with leadership from across campus. And again, the DNA and the values of this center, which I hope you will also get through my talk, is truly to bring technologies and applications and human experience together to build a better world for all. I think this is something that we need to be responsible for and can achieve. Okay, so that's the URL. If you want to know more, we have a white paper that describes a lot of our vision, what the challenges are in more detail, et cetera. I'm not going to have time to go through all of that here, obviously, but I'll just give you a glimpse of what the high-level themes of the center are, and then dive down into parts of it. Okay, so under technologies, we have 3 themes, and as you can imagine, and no surprise given who the speaker is, the first theme is about co-design in the post-Moore era. Right? I talked about all of those aspects that need to be brought together, chips to systems and beyond. How do you build systems that co-design across the stack? The second is harnessing AI, which I think needs no explanation here. It's changing how we think about immersive systems from the ground up. So that's a big part of the center. And the third, which I think is really going to be transformative, and we all need to work on this, especially this community, is the science of design. So as I said, the human experience is a big part of this continuum here. How do we design systems that are co-designed across the stack driven by the human experience? We don't have a science to do that, and that's what we are after here. In terms of the types of activities we do in this center, this is truly integrative research, bringing together people. We want to build open source test beds and infrastructure that we make available to the entire community, and do technology transition. I should say that Immerse itself is a catalyst to enable all of this. Under applications, we have identified, we work on all sorts of applications, but we've identified two main applications of focus. One is healthcare and the other is education, for reasons that you might have guessed from the initial slides. We have a lot of strengths there, and so we want to exploit that, but we do work in all sorts of applications in the center. And finally, what we would like to do is build an application development ecosystem so that we can provide an agile ecosystem for people to write applications quickly. And again, a lot of this is integrative and open work, including providing infrastructure for others as well. In human experiences, we have work in the experiential part, in the contextual part, in the social part that I described. And again, we want to be able to democratize the use of user studies and figure out how to do this type of research in the context of technologies and applications. So that's a brief overview of Immerse. And a lot of my work is inspired by this vision. So next, I'm going to dive down a little bit more into the technologies part, since that's a big part of who we all are. So a common theme, as you heard, is that we want to have co-design. Again, chips to systems is the mantra here, so I'm preaching to the choir. But it's not just one system. The potential here is for collaborative experiences, and so we are looking at a distributed system with not just the headset or the edge or the user device, but the edge and the cloud. How do you harness the power of all of this together so that we maximize the user's human experience? Okay, so again, the common theme here is that we want to have a human experience-driven, full system type of research agenda, enabling new applications. And by human experience, again, we're talking about a multimodal experience, so that we are talking about vision, we're talking about audio, haptics, and this is the one technology where we can really hurt ourselves, right? So you can have headaches, nausea, et cetera. So we want to be able to use that human experience to drive our systems. So this was great. Vision, when we started, was very, very exciting. But unfortunately, when we started working on this vision several years ago, we found that progress was really hard. And that was because there were no open source systems or benchmarks for people like us. Right? How do you do research in an area talking about full system design when there's no open anything to start with and to benchmark and to drive your work? This is a large barrier to entry for open R&D, and so that's why we did a pivot for a while and started to build this open infrastructure. So this is the effort of a lot of people, lots of students, consultations with industry and academic colleagues. There's a long list of names that I will not go through, but just to say that this is really a lot of people coming together. So this is what led to Elixir, which is the Illinois Extended Reality Testbed. Today, this is an open source, full system XR testbed. It has state-of-the-art XR components with a modular runtime. It's compatible with a standard that developed concurrently while we were working on Elixir called OpenXR, which is an open standard for, that provides an interface between applications and the XR runtime so that you can democratize application writing for XR systems. So this was great for us. And we established a community consortium to democratize research and development and benchmarking in this area. So we've used Elixir, as you will see, extensively for characterizing XR systems as well as for a lot of research. And by we, I mean not just my group, but the community. Okay, so just to give a sense of what Elixir looks like, how we use it day to day, you don't have to have a headset walking around all the time. Here in the gray box there, I have my student walking around with cameras and IMUs. The left or your right is showing the virtual space that the student is traversing with the headset showing where the student is, and the right side is the actual pixels that Elixir is generating. And then there's a lot of debug support in the debug windows, et cetera. And so this is how we do our day-to-day research. But then we can also have a real headset experience where here in this very novel contraption, one student is walking around with a PC because a lot of what we do cannot be computed on embedded class systems. And so he's walking around with a PC, and the headset that the other student is using is being used entirely as a display. So Elixir is running on the PC and sending the images to be displayed on the headset. And on the right, you see the student, the virtual space that the student is walking around in, and it tracks well, renders well, et cetera. So this is completely open source, right? You can go and modify any part that you want, and any measure. There's a lot of telemetry. You can measure lots of things, as I will show you, and enjoy and plug and play new components, et cetera. So if my student loses their buddy, we moved Elixir to a backpack PC, and now they can walk around free. All right, so here is digging a little bit more deep into Elixir. Just like any XR system, there are three broad components or pipelines. The perception pipeline, which basically says where the user is in the world, what does the world look like around them. So this has the sensors, the cameras, the IMUs, head tracking, in our case through visual inertial odometry or VIO, an IMU integrator, eye tracking, scene reconstruction, et cetera. And then we have the visual pipeline, which is the part of the system that takes the perception information, takes what the application wants to do, and generates the pixels that the user is going to see. And this includes reprojection, holography, et cetera. And then we have the audio pipeline that produces 3D spatial audio. So we have encoding there as well as 3D spatial audio playback. So I don't have the time to go through all of these in detail today. There's lots of information available on our website through videos, papers, et cetera. And on top of Elixir, now we can run OpenXR applications, so Unreal, Godot game engines, et cetera. And so today, all this stuff in orange primarily runs in software, okay? And this software runs on a mobile device like Jetson, et cetera. And so you have your whole XR system stack. Now, a lot of what we are doing, of course, is also trying to figure out what to put in hardware, and that's a big part of the research agenda that I will talk about. And not only what to accelerate in hardware on the system, but as you will see, there's just it's very hard for me to imagine that the kind of experiences we're going to talk about, we will be able to fit all that compute in this headset form factor. And so we are going to have to offload a bunch of it to either something in your pocket or a server at the edge or the cloud. How do you do this type of offloading? So Elixir now has the ability to offload several components. Okay. So again, I want to stress that Elixir is not just a collection of these different components. It's not just a collection of a head tracking benchmark and a reprojection benchmark, et cetera. It is a full system. So here is the system's data flow. There's IMUs that run at very high frequency to produce inaccurate but fast head poses. There's the camera that's used for more accurate but slow head poses through computer vision algorithms like the VIO, which takes both the IMU and the camera information. There's the IMU integrator that produces fast and correct poses all the time for the system. There's eye tracking. There's reconstruction that takes camera images, application that does rendering, uses all of this information, reprojection, then you make sure that the frame is rendered for the time that, or the frame is reprojected for the time and the head pose that we estimate will be the case in the future. It's hologram, there's audio, and so on and so forth. So the details are not important for the purpose of this talk. The point is that there is a lot going on in the system, not just in terms of the individual components, but how they all work together. And Elixir provides a runtime that achieves all this, the different components running at different frequencies, multiple interacting pipelines. There are synchronous and asynchronous dependencies that Elixir keeps track of, and it provides multiple quality of experience metrics. So the nice thing, we put a lot of effort in making sure that this was a very modular and flexible architecture. And so Elixir components are just plugins. You can separately compile and dynamically load them and swap in different algorithms for different parts of Elixir, and it works relatively painlessly, right? It's a fairly complex system, so you do have to put in some effort, but it's relatively painless to swap things in and out. And at the same time, it's very efficient and provides a flexible communication interface. So it's an end-to-end system that balances flexibility with efficiency. For applications, I think I already mentioned this. We use Godot and Unreal Game Engine. Anything written on those, we can run on Elixir. We compute several end-to-end quality metrics, all of the state-of-the-art metrics. And then, so using all of this, so we built all this infrastructure. It took us a while. And then we used it to characterize various parts of an XR system to figure out, where are really the bottlenecks in a scientific way and what type of research we need to do. So our findings, again, I don't have the time to go through it in detail, but just suffice to say that we have lots of data on frame rates, on execution time and distribution of different components of the system, of power for different components of the system, and the quality of experience metrics. So these are the first published power, performance, and quality of experience results for an end-to-end XR system. Okay. So here's the important part. So we did all this work, and what were the implications, right? What did we find? And these implications essentially set the agenda, at least for my research group, for the next very many years, and hopefully you will find this interesting as well and join us. So first thing we found, yes, there's substantial performance, power, and quality of experience gap. So we need to accelerate, specialize not just the hardware, but the software across the device edge cloud continuum. There is no doubt about that. But another interesting thing was that no application component dominated all the metrics. And so we really need to consider all the components of the system together. If one was performance sensitive or power sensitive, another affected the quality of experience a lot more. And so everything needed to be looked at together. Power consumption, as you can imagine in this group, I think it's easy to imagine this, goes beyond just the CPU, GPU, DDR. We need to consider the system level components, the sensors, the display, the I/O, et cetera. And then there's significant variability in these components. So we need to very intelligently partition, allocate, and schedule the system resources at runtime. Finally, this was more surprising. We sort of expected this, but it was really surprising to what great a degree this actually happened. That the per component metrics do not really capture the quality of experience. We're of course used to using PPA. PPA doesn't really mean that much in this domain. Well, it's important, of course, but then you also want to know how this translates into how the user would perceive these, what you just designed. And looking at this at a per component level did not tell us what the end user's experience would be. And so we really need to look at the entire system to make quality of experience driven trade-offs. So those were system level implications. And we did a whole bunch of work on per component design and per component analysis. And here we found even within a component, there's an abundance of tasks. No single task dominates. And so it's not very, you can't just look at the system and say accelerate this and accelerate that. We need to have automated techniques to figure out what to accelerate. It's impractical to build an accelerator for every task here. We need to build shared hardware. How do we go about doing that? There's a huge diversity of compute and memory primitives. How do we build these flexible systems? And then most importantly, these algorithms are in flux. I mean, every 6 months there's something brand new. There's a new scene representation. There's a new neural algorithm. How do we bring all of that in and keep this system working for everything that's happening? So we need to design programmable hardware that can be changed to adapt to the rapid change that we see around us. And then finally, different algorithms have different, have a variety, or like a large space of QoE versus resource usage trade-offs. How do you take advantage of that? This is a huge knob that is still not fully exploited, and I will make the case later to exploit this. So this is a very rich playground for systems research, and I hope that you would join in exploring this playground. There's been a lot of research that Elixir has enabled, not just in my group, but others as well. There's a lot of ongoing work going on. Today, I'm not able to describe all of this. What I've done is picked 2 examples. One is for hardware acceleration, and the other is to show the impact of cross-component QoE-driven co-design. Okay, so for hardware acceleration, one of the things that, the first thing that was evident to us that I also emphasized earlier was that there is a huge diversity of tasks and there's many of them. Okay, so we could build coarse-grained monolithic accelerators per task, or we could identify common finer-grained primitives that are reused and build these fine-grained disaggregated accelerators for these primitives and then compose them on demand. So this was work that we did to figure out what are the trade-offs and how do we build hardware with these disaggregated accelerators. The trade-offs, I think this community will, these are kind of obvious, that for a monolithic accelerator, the design cost, the utilization, the leakage, the extensibility are compromises that you have to make compared to the disaggregated version. But with the disaggregated version, the control and data tax are much, much higher than monolithic. By control, I mean the cost to invoke the accelerator. Every time you want to invoke a fine-grained accelerator, you're paying a cost, and that cost gets multiplied because now you have these smaller accelerators. And then there's the data tax, which is the cost of moving the data to from accelerators. So what we did was develop a system called Mozart that tries to get the best of both worlds. And so the idea is to tame these data and control taxes and be able to compose accelerators seamlessly. The key insight here is to use the shared memory paradigm that is becoming very common now in SoCs. And so for the control tax, the baseline is where typically accelerators are invoked with bulky OS calls, and the CPU mediates this orchestration. So what we did was provide a simple, very lightweight implementation of a synchronization interface. So we call this an accelerator synchronization interface that uses shared memory, very low overhead, and the really cool thing about this is that it allows us to treat accelerators as first-class citizens. And so accelerators can now synchronize with each other through shared memory in a transparent way, just like they were a CPU, and we can have chaining between accelerators, pipelining between accelerators without the CPU mediation, and this composition of accelerators is completely transparent to the CPU. It's all software programmable. For the data tax, one of the big problems with using shared memory has traditionally been that coherence is generally expensive for an energy efficient, for a system where energy is a big driver. Using messy-based protocols, there's lots of extra traffic and so on. So we developed a coherence protocol called Spandex, which is a very lightweight protocol that specializes based on the behavior of the accesses, and especially for producer-consumer chains, which is what a lot of XR workloads are. It ensures very lightweight, direct accelerator-to-accelerator movement without specialized paths. So this is just all through shared memory in a coherent way, so it's programmable, et cetera. I don't have the time to go through all of the details, but just to give us sort of a pictorial sense, with Mozart, if you bring these two ideas together, you essentially are going from accelerator to accelerator without additional CPU overhead, streamlined data communications, streamlined control, and here are some results for one of the Elixir workloads. So we took the 3D spatial audio decoder from Elixir. There's lots of results in the paper that I referenced earlier. In this one, we took the 3D spatial audio decoder. We built a monolithic accelerator for it. We built a disaggregated accelerator for it using 3 of the common primitives that this decoder had. And the baseline, if we didn't apply our ideas, of course, showed that disaggregated was twice as worse as the monolithic, which is no way is anybody going to build this kind of thing then, in spite of the advantages of IP, et cetera, for the disaggregated. But then when we applied Mozart and chained the accelerators just through shared memory, no extra hardware for chaining, we closed the gap. Monolithic also improved because it can also use our ideas, but the gap closes, and then when you do pipelining, the gap closes even further. And so Mozart closes the gap between monolithic and disaggregated with accelerator pipelining. And so this now gives us a framework and a foundation to use these composable fine-grained accelerator techniques to start thinking about a full XR SoC architecture. But of course, it's not just about how do you build the architecture, but questions about what are you going to accelerate, and what are you going to do on chip, on the device, versus what are you going to offload? So all of that analysis and the machinery for that doesn't exist yet. We have some initial results in a text paper that we published last year. We are using some compiler techniques to help us out with this, but we still have a long way to go. Plus, now that this hardware is all shared between multiple components and needs to be scheduled at different frequencies, et cetera, that you saw, there's a lot of scheduling work that needs to be done for this. We have some preliminary results for that. But again, a lot needs to be done. And then the big question is how do you, the results I showed were for one component. But I mentioned earlier, we want to be able to do cross-component co-design. We want to be able to do device edge cloud distributed accelerator co-design. How do we go about doing that? And then how do we go about incorporating all of the rapid advances that are happening right now? So the neural models for reconstruction, editing, simulation, and rendering are all changing. Every few months, something new. How do we rethink the perception and visual pipelines for acceleration and offload partitioning? So these are all big questions, many PhD theses in here. So the second thing that I want to quickly talk about is cross-component QoE-driven co-design. And we use this for gaze track foveated rendering. So foveated rendering is based on the observation that rendering is a very expensive thing in these XR systems. And with foveated rendering, you render, ideally you have a gaze tracker, so you know where the user is looking, and you render at high quality just in the fovea region where the user is looking. And, but the problem with this is that well, the good thing is you reduce rendering energy because the high quality rendering is in a small space, but the gaze tracking takes up energy, and there's a strict motion to photon latency that might be violated if you're waiting for the gaze tracker. So instead, a lot of the products employ fixed foveation, where you assume that the user is always looking in the center of the frame, and that's where you apply foveation. So this is great because you don't need gaze overheads, and unfortunately, it has a little bit higher rendering energy because you are now going to use a larger fovea, because of course the user is not going to be looking at the center all the time. However, you're not going to be rendering the whole thing at a high quality, and so there's suboptimal quality if the user is not really looking close to the center. And so just to summarize, with track foveation, we have an energy problem because of gaze prediction, but higher quality. With fixed foveation, the energy problem is under control, but low quality. And so what we looked at was, how do we do end-to-end co-design foveated rendering? Instead of looking at just the gaze prediction and trying to optimize that for energy, we said, okay, let's take the gaze predictor network, optimize it, the heck out of it. But what this does is and that gives us 20x energy and 9x latency savings, but it introduces error. And so what we did was we mitigated that error by changing the fovea size slightly in the foveated rendering case. And this recovered the QoE. And by using this co-design, these were the first results to show that tracked foveation can actually be more efficient, energy efficient than fixed foveation. The other interesting thing was that because we had this system, we could look at the headset, we found that the metrics that were used, these are state-of-the-art metrics that were used to measure the impact of foveation, which is super important here because the name of the game here is that we are playing around with the quality, right? We are taking guesses about how large the fovea should be, et cetera, et cetera. So the metric did not match the user experience. This is a story that repeats itself. We've done a whole bunch of other work on edge cloud offloading, and the same story repeats. The metrics don't match the experience that we get from our end-to-end system. So many questions arise, right? How do we automate this cross-component co-design? I just showed two examples. We've done work in other cross-component co-design, and I'm happy to refer you to those papers. But how do you automate this? This is not something you want to do manually. How do you get strong application-specific QoE metrics? The current gold standard in these systems is user studies. But user studies are really, really hard to deploy. To do a full design space exploration with user studies is just crazy. Takes too much time, too expensive, needs too many users to get statistical significance. And moreover, the experiences we found vary significantly with the application. If I'm doing surgery versus walking around in a park using my headset, well, the requirements are different. Based on the user, the experience is different. So how do we reduce this design, test, refine, cycle time that gets so blown up when we are using these user studies? And without the user studies, it's really hard to exploit that large trade-off space that we have between latency, energy, and accuracy in these systems. How do you enable this fast design space exploration? And that's really one of the key issues that we are grappling with and we are working on. So to wrap everything up, here are some of the high-order bits that I would like you to take from this talk. These are the implications for immersive system design that we've seen. We really need to do full system co-design. I didn't talk much about the edge cloud work. We have a lot of results on that. I'm happy to share. I talked about within the device, how do you do per component, cross-component co-design. But we do need, there is too much on the table here to give up to not do this co-design. The experience is application-specific and user-specific. How do we bring that into the design loop? We need user studies for full experience, but these are too hard. How do we get around these? What we need is really a new science of design for these systems. And I think this community can play a huge role. We're really about chips to systems. We need to also bring the human in and get a new science going. So our grand challenge is comfortable, mobile, all-day, trustworthy, rich immersive experiences. This has the potential to transform all human activities, but we need a new science for designing such systems, for meeting this grand challenge. We are taking a step through the Immerse Center, bringing together immersive technologies, applications in the human experience, and through Elixir, trying to democratize systems research by building open infrastructure for people to experiment. So I will stop here.